As you can remember, on our previous lessons, we have learned some facts about electric current, and as it derives from the experiments, there is interaction. There is interaction between electric current, and magnetic field, and moreover, electric current always produces magnetic field. And magnetic field can also be produced with magnets. And it is necessary to say a few words about magnet. As you maybe know, magnet each magnet has two poles. Every magnet always has two poles. They are known as south pole and north pole. And lines of magnetic field can be drawn in this way, with these red arrows. These are lines of magnetic field, and lines of magnetic field are always closed lines. They are always closed lines of magnetic field, and it is necessary to say that it is impossible to find or to create a magnet that has only one pole. So every magnet has two poles. South and north. It always has two poles, south pole and north pole, and this is a fundamental property of magnetic field. This is difference between electrostatic field and magnetic field. Lines of electrostatic field can begin or end on electric charges, and lines of magnetic field have no begin and have no end. So they are closed lines. Okay, so how to measure or how to detect, how to observe magnetic field? It can be done with a small circuit, with electric current. A small circuit for electric current. Let's imagine that we have electric current. In a little circuit. I'll show this on a picture. Circuit with electric current. E. With electric current I. And this circuit is perpendicular to the screen, and the part of this circuit that is behind the screen, I'll show with dash line. So dash line is part of this current that is behind the screen. That is behind the screen. It is because it is necessary. It is necessary to understand. Okay, and what can we say about this? The normal vector to this circuit can be drawn here. This is normal vector or vector of normality. Vector of normality to this circuit can be written as n. Absolute value as n is equal to 1. And we can write so-called magnetic moment for this circuit. Magnetic moment has the same direction as unit vector of normality. This is magnetic moment, and connection between magnetic moment and current is this connection is simple. So connection of magnetic moment is this I S, where S is area of this circuit with electric current, and here we have vector n, vector of normality. So I have written a formula for magnetic moment. Magnetic moment. Magnetic magnetic moment. Magnetic moment. So here we have magnetic moment. Magnetic moment that is necessary to observe magnetic field. Magnetic field. I will tell about this a little bit later. Okay, and so this circuit with magnetic moment allows us to observe magnetic field. So it is necessary to say a few words about magnetic field and how to evaluate this field. How to define this, and so the main values to define magnetic field are magnetic induction vector, and magnetic field intensity, and magnetic induction is can be written as vector B. This is magnetic induction vector. Units for magnetic induction are Teslas. Tesla is a unit for magnetic induction. Tesla is a unit for magnetic induction. And magnetic field intensity. Is H vector, and units for H vector are amperes divided by meters. Units for magnetic field for magnetic field intensity. And there is connection between these two values. This connection is mu 0 and multiplied by h. Multiplied by h. So what can we say about this? B is a vector of magnetic induction. Magnetic induction. A vector of magnetic induction. A vector of magnetic induction. Okay, and H is a vector of electric magnetic magnetic field intensity. Intensity is a vector of magnetic field intensity. Is a vector of magnetic field intensity. Vector of magnetic field intensity. Okay, and what is mu? What is mu? So mu is magnetic magnetic relative permeability. Relative permeability is relative permeability. And it is important for vacuum. For vacuum mu is equal to 1. 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 And mu 0. Mu 0 is a permeability of free space, or vacuum magnetic permeability or magnetic constant is magnetic constant. Sorry, it is necessary to write its value first. So it is equal to 4 multiplied by p and multiplied by 10 to the power of minus 7 Henry divided by meters. And this is magnetic constant. Or vacuum magnetic permeability or vacuum magnetic permeability, or permeability of free space. Or permeability of free space. Or permeability of free space. So this is the same values. And often instead of mu, may be used another value, he, for example, we can write that mu is equal to he plus 1, and where he I will write this where he Greek letter he is magnetic susceptibility, is magnetic susceptibility, and for vacuum this value he is equal to 0. For vacuum he is equal to 0. For vacuum he is equal to 0. Vacuum he is equal to 0. So these values can be used to define magnetic field. These values are enough to define magnetic field. So we can use magnetic induction. We can use magnetic field intensity. We can use magnetic field intensity H to define magnetic field. And the next question is to define the interaction between magnetic moment and magnetic induction and magnetic field. So for this we can write that moment. We can write that moment of force, moment of force that acts on magnetic moment from that acts on magnetic moment in magnetic field, field. There is a direct connection. And this connection can be defined with a formula. And according to this formula, mu is equal to P m Pm multiplied by Pm multiplied by B multiplied by B multiplied by vector of magnetic induction. Vector of magnetic induction. Okay, do you have any questions about this? No questions. Okay, if there are no questions, it is necessary to say that there were conducted a lot of experiments, and these experiments have shown that magnetic field that is produced by any conductor can be calculated with Biot-Savart law. Can be calculated with Biot-Savart law. So let's write this law. Let's write this law. Biot-Savart law. Biot and Savart are French names, French surnames. So and it means that we have some interesting way of writing these names, and this law can be written for linear current. This law can be written with formula differential B is equal to mu 0 divided by 4p and electric current and here we have dl I will write lower index c. Lower index c means that dl is a part of conductor. dl is a part of conductor. And multiplied by vector r and divided by r to the power of 3. Okay, and very similar formula we can write for vector dh. Similar formula. So I can write just dh is equal to and it is necessary just remove this mu 0 and write 1 divided by 4p 1 divided by 4p divided by 4 and p. So this is Biot-Savart law, classic in its classic form for linear current. Okay, and I will make a picture to to explain this formula. Okay, so let's make a picture. For example, if we have linear current, for example, with current E, the infinitely small element of this current is vector dlc. So this is vector dl. This is vector dlc. And what is vector r? R is a vector that begins in the beginning of vector dlc and ends in point where we want to calculate magnetic field. So here we have vector r. This is vector r, and according to the properties of cross product, here we will have magnetic induction vector. Magnetic induction vector in this point will be directed from us to the screen. Vector B will be directed from us to the screen. Okay, here we can define angle between these two vectors, this angle alpha, and the line of magnetic field. Line of magnetic field can be written in this way. Well, this is line of magnetic field. Line of magnetic field. It is always closed line. And so I can. It's necessary to make here dash line. Dash line is part of a line of magnetic field that is behind the electric current. So dash line is behind the electric current. So this red line is line of magnetic field on this sketch. Okay, and what can we say in this case? For absolute value of magnetic field or magnetic field induction or magnetic induction, for absolute value we can write that dB is equal to mu 0 divided by 4p electric current dLc divided by r to the power of 2 and sinus alpha. This is formula for absolute value of magnetic induction and it can be derived directly from Biot-Savart law. It can be derived directly from Biot-Savart law. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions, let's try to write Biot-Savart law for electric current density. To do this, I will draw an infinitely small cylinder. An infinitely small cylinder to do this. And I'll draw this cylinder. With dash line because this cylinder is not something real. It is just geometric. Is just geometrical object. It is not something. It is not something that is real. And because of this fact, I'll draw this dash line. And this cylinder is infinitely small. And the axis of this cylinder has the same direction. Of electric current density. This cylinder has the same direction as electric current density. And the base of this cylinder has area ds. That can be defined with vector ds. And the height of this cylinder, is dlc. This is dlc. And it is also necessary to define a vector dlc. And absolute value of this vector, modulus of this vector, is equal to the height of the cylinder. It is equal to the height of the cylinder. dlc. Okay, and for this picture, we can write that electric current density has the same direction as vector ds. And it has the same direction. As vector dlc. Okay, and let's try to write. Let's try to use Biot-Savart law for this infinitely small cylinder with electric current. Let's try to do this. I'll use this formula. I'll use this formula to do this. So what can we say about electric current? First of all, electric current I it is number. So it can be written inside inside this square bracket. So I can write that I can write this inside a cross product, inside the cross product, and here we have DLC multiplied by R and close bracket and divided by R to the power of 3. By R to the power of 3. Okay, and what can we write from here? As you know from our previous lecture, electric current is equal to electric current density multiplied by ds dot product dot product of electric current density and ds. And there is no integral. There is no integral because the cylinder is infinitely small. Because the cylinder is infinitely small, and because of this fact, there is no integral in this formula. So from here we have that we can write and moreover we can it is necessary to say one more thing that it's necessary to say one more thing that because vectors j and ds have the same direction. Because of this, we can make conclusion that this scalar product can be rewritten with only its moduluses. So we can write this formula in such way. Okay, do you have any questions about this? No questions. Okay, if there are no questions, let's continue. So from here we have that J, ds, J and ds, and DLC multiplied by R and divided by R to the power of 3. Divided by R to the power of 3. R to the power of 3. Okay, and from this we can write that vector J, absolute value of vector J multiplied by vector DLC, and this can be written as a vector of electric current density multiplied by absolute value of DLC. This is result of the same direction of vectors J and DLC. Okay, and from this we can write that we can write that here we have mu and J vector of electric current density multiplied by R and multiplied by ds and DLC and R to the power of 3. R to the power of 3. And as we can see, ds multiplied by DLC is a product of area of base of cylinder and the height of cylinder. And as you know from school, this will be the volume of the cylinder. It will be the volume of the cylinder. So from here we have formula of Biot-Savart law. Formula of Biot-Savart law, dr, and multiplied by the differential of the volume divided by r to the power of 3. Divided by r to the power of 3. Divided by r to the power of 3. Okay, do you have any questions about this? No questions. No questions. Okay, if there are no questions, I will remove some unnecessary things, from the screen, in order to free some place on the screen, and I'll write the final conclusion. Of this. I'll write the final conclusion of this. So in this case we have Biot-Savart law. Biot-Savart law for electric current density. For electric current density. Biot-Savart law for electric current density. And similar formula can be written for the vector of magnetic field intensity. So we can write very similar formula, but it is necessary to change mu 0 with unit, with 1. So it is necessary to remove this and to write 1. Okay, do you have any questions about this? No questions. Okay, if there are no questions, we can remember that electric current density is from our previous lesson. This is elementary charge, E plus, multiplied by concentration of electric charges, concentration of elementary charges inside a conductor, and multiplied by average velocity of electric charges. Average velocity of electric charges. And this concentration is concentration N is equal to it is equal to number of electric charges dN divided by volume dV, divided by volume divided by volume divided by volume of divided by volume divided by volume and multiplied by average velocity. And product of number of electric elementary charges and the value of elementary charge will be charge Q divided by dV and multiplied by U. Okay, and we can make substitution. We can make substitution, and from this we will obtain that dB is equal to mu 0 divided by 4p divided by 4p. Here we have dq and u multiplied by r multiplied by r and divided by r to the power of 3. Divided by r to the power of 3. So we have obtained Biot-Savart law for a point charge in motion. For a point charge in motion. So we can write Biot-Savart law and Biot-Savart law for a point charge in motion. For a point charge in motion. So it can be written as B, vector of magnetic induction, that is, it is equal to mu 0 divided by 4p and charge Q multiplied by V, so velocity of electric charge, and V and R. R is a vector that begins in point charge and ends in point where we want to calculate magnetic field. We want to calculate magnetic field. Okay, and the same for vector H. The same for vector H will be defined with this formula. this formula, but it's necessary to remove mu zero and to leave just only one. Just only one. Okay, do you have any questions? No questions. And it is necessary to say that for magnetic field, we also have a superposition principle. For magnetic field, we also have a superposition principle. Superposition principle for magnetic field. So superposition principle. Superposition principle for magnetic field. For magnetic field. Superposition principle for magnetic field. It is also a result of experiment, and it can be written as just as vector sum of magnetic fields. So superposition principle, and of course, the same situation is for vector of magnetic field intensity. The same situation as for vector of magnetic induction. And this superposition principle and Biot-Savart law are enough to define magnetic field of any system of conductors. So to define magnetic field for any system of conductors, we should know Biot-Savart law and superposition principle for magnetic field. And it is also necessary to say that as you can remember for electrostatic field we have that integral along closed line of E dl. So I wrote dr on our previous lessons, but now I will change this with dl. It doesn't matter, but it is more useful in this case to write dl. And this integral for electrostatic field is equal to 0. Okay, and what about magnetic field? What about magnetic field? And for magnetic field, we will have another situation. We will have for magnetic field that this integral b dl b dl. So this integral for magnetic field can be written. This integral for magnetic field can be written as mu zero and the sum sum of electric currents. Sum of electric currents that passes through closed line L. So this is sum of electric currents that passes through closed line L. What about electric currents that don't pass through this closed line? For this current, here will be 0. For electric currents that don't pass through closed line L. For closed line L. Okay, and the similar is for vector H. The similar is for vector H. HDL, and this is equal. This is equal to just sum of I. Just sum of I. Okay, and what about electric current density? For electric current density, we have very similar formula, but it will be surface integral instead of sum. So SL is surface inside closed line L. And here we have electric current density and ds. Okay, and for vector H, the situation is very similar. dl. The situation is very similar, but here we have just surface integral as a surface inside closed line L, J ds. So this is one of main properties of magnetic field, and these properties mean that magnetic field is not potential. It is not potential. This is a difference between magnetic field, for example, and electrostatic field. So, and this formula are known as Ampere's circuital law. Ampere's circuital law. When electric field maybe just in Ampere's circuital law in integral form. Ampere's circuital law in integral form. Ampere's circuital law in integral form. And of course, if we have integral form, we must also have differential form. And differential form can be written in the next way. So Ampere's Ampere's circuital law in differential form. Ampere's circuital law in differential form can be written in the next way. It can be written as it can be written as rotor. Can be written as rotor B. Rotor B, and it will be mu. And now I will explain this now, and multiplied by electric current density, or it can also be written as rotor. Can also be written as rotor H. Rotor H, and it will be equal electric current density. Will be equal electric current density. It will be equal to the electric current density. Okay, and what is rotor? Rotor is a vector differential operator. Rotor rotor B, for example, is the same as this is the same as Carl B. This is the same. This is the same, and this is the same as this is the same as this is the same as vector product of del operator multiplied by B, and this is the same as I yod key and here it is necessary to write that here we have d dx, d dy, and d dz. Here we have determinant. Three by three dimensions, three-dimensional determinant, and here we have b x, b y, and b z, and it will be equal in extended form. It can be written d b z by d y minus d b y and dz multiplied by ort I plus d b x by d z minus d b z dx yod and plus d dby and dx minus dbx dy. Okay, and this is Carl or rotor operator. So I have written this in extended form to understand what does it mean. To understand what does it mean. Okay, do you have any questions? Do you have any questions about Ampere's circuital law? Do you have any questions? No questions. No questions. Okay, and as you can remember, for electrostatic field, we have for electrostatic field we have Gauss flux theorem for electrostatic field. For electrostatic field, we have Gauss flux theorem that can be written as surface integral of and ds, and this is equal to qs divided by epsilon 0. Gauss flux theorem for electrostatic field. For electrostatic field. What about magnetic field? If we will write if we write this integral for magnetic field, for magnetic field, in the right side, in the right side of this formula must be magnetic charge, inside closed surface S. But we have said before that there are no magnetic charges. There are no magnetic charges with just one pole, south or north. And this means that we have zero in right side of magnetic for Gauss flux theorem. So Gauss flux theorem or Gauss law for magnetism, So here we have Gauss law for magnetism, or I will write integral form of or Gauss law for magnetism. integral form or Gauss law for magnetism. And in the same way, we can write differential form. Differential form of Gauss law for magnetism. And it will be just divergence. It will be just divergence. We have talked about divergence on our previous lessons. Divergence B is equal to 0. 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 Okay, do you have any questions? No questions. No questions. Okay, and what about force of interaction? Force of interaction between magnetic field and electric current. What about force of interaction between magnetic field and electric current? It can be defined. It can be defined with Ampere's force law. Ampere's force law. So Ampere's force law. A little time ago we have learned Ampere's circuital law, and now it is necessary to write Ampere's force law. So Ampere's force between magnetic field and element of conductor DLC can be written in this way. Can be written in this way. Ampere's force law, and similar it can be written for electric current density. So Ampere's force law for electric current density. For electric current density, it will be dF is equal to electric current density J multiplied by B and multiplied by dV. It can be proved with Ampere's force law in a similar way as we have done before for Biot-Savart law for electric current density. Okay, and what about point charge? What about point charge? For point charge, it will be Lorentz force. It will be Lorentz force. It will be Lorentz force. So it can be written in the next way. So Lorentz force If we have both electric and magnetic fields, Lorentz force will be F is equal to Q E plus Q multiplied by velocity of charge Q multiplied by magnetic induction vector. Magnetic induction vector. Vector of magnetic induction. Vector of magnetic induction. Okay, what questions do you have about this? No questions. No questions. Okay, and the next question is how to define the direction of Ampere's force or Lorentz force. It can be done with the left hand rule. Let's imagine our left hand. Let's imagine our left hand. Let's imagine our left hand, and the magnetic induction vector should be directed to the palm. Magnetic induction vector should be directed to the palm. So vector B is directed to the palm, and the direction of positive charge velocity or direction of electric current density and the direction of electric current must be this. And in this case, the thumb of our left hand will show the direction of Ampere's and Lorentz forces. So force will be here. So this is left hand rule. Okay, what questions do you have? What questions do you have? No questions. Okay, if there are no questions, thank you for your attention. Thank you for your attention, and I hope to meet you next week.